Okay, let's dive in. Black holes, right?
Mm-hmm.
You hear the name, and you picture this ultimate cosmic drain just hoovering up everything in sight.
The ultimate vacuum cleaner, yeah.
Exactly. But have you ever stopped to really think about what falling in actually means? Like, is it just lights out, game over?
Uh-huh.
Or is there something, I don't know, more bizarre going on at the edge of forever?
Well, it's funny because that seemingly simple question, what happens when something disappears into a black hole?
Yeah, where does it go?
It actually unravels into some of the most profound mysteries we have about the universe. We're
Yeah.
really talking about the intersection of gravity, quantum mechanics,
Then information, right?
and the very nature of information itself. Yeah.
Exactly. And for this deep dive, we're looking at a source that gives us an introduction to these, well, mind-bending concepts.
Black holes, information, string theory. It touches on it all.
Yeah, think of it as your cheat sheet to some seriously advanced cosmic thinking.
Good way to put it.
So our goal today, our mission, is to pull out the crucial insights about what black holes are and how they interact with stuff, without needing a PhD to follow along.
Right. Hitting the key concepts. We're hunting for those aha moments.
Those moments that make you see the universe just a little differently.
A fantastic goal. So, where should we start? Maybe tackle this idea that they're totally inescapable.
Yeah, good idea. Because while it's true that beyond a certain point, the pull is overwhelming.
The point of no return.
Right. But it's not quite a simple one-way street for everything that just gets close, is it?
No, exactly. That image of everything just getting sucked in immediately is a bit too simplistic.
Okay. Our source mentions a potential barrier around a black hole. Can you maybe paint a picture of what that is?
So think of it like this. Imagine trying to roll a ball up a hill.
All right.
The hill, that's kind of like the black hole's gravity. It's a
Okay,
pull,
the slope.
right? And to get the ball over the top into the black hole on the other side, it needs enough push, right? Enough
Okay.
energy.
To get over the crest.
Exactly. That crest is like this potential barrier we're talking about.
Got it.
And here's the quantum weirdness. Even if the ball doesn't quite have enough energy to roll over the top,
Uh-huh.
there's still this tiny, tiny chance it can just, tunnel straight through the hill.
Quantum tunneling. Still sounds like science fiction.
It feels like it, but it's real.
So even if a particle doesn't have the raw energy to escape directly, it could sort of ghost its way out.
In a probabilistic sense, yes. Our source specifically talks about wave quanta.
Okay, what are those?
They're basically fundamental particles that have no spin, zero angular momentum.
Simple particles.
Very simple. For them to get over this gravity hill, they need a certain minimum energy. It's actually tied to the black hole's mass.
Okay.
If they have less energy than that threshold, well, they're more likely to have to tunnel through.
So it's like a very, very improbable escape route, but it exists.
But it exists, yeah. Quantum mechanics allows for it.
Now, what about particles that do have spin? Angular momentum. Is it easier or harder for them?
It's actually much harder for them.
Really? Harder?
Yeah, the potential barrier, that hill we talked about, it's
Yeah.
effectively higher for particles that are spinning.
Huh. So the hill gets steeper.
Pretty much. So if our ball is spinning rapidly, it makes it even tougher to roll away from the black hole.
Wow, that's counterintuitive. You'd think spinning might, I don't know, fling it away or something.
You might think that, but nope. The physics says it's harder for spinning things to escape the black hole's clutches.
Interesting. Okay. Now let's shift to something else that always seemed deeply strange to me. Hawking radiation.
Ah, yes. A big one.
The idea that black holes aren't completely black.
It is deeply strange, and it was a truly revolutionary idea from Stephen Hawking.
Right, so they're not just passive absorbers.
No, it turns out they constantly emit this very, very faint thermal radiation.
Thermal radiation, like heat.
Essentially, yes. Think of the black hole less like a perfect drain and more like a slightly leaky container.
Leaky.
Yeah, holding a tiny, tiny amount of heat or thermal energy.
A leaky black hole that glows faintly. That's a powerful image. So what exactly is leaking out?
Well, it's related to quantum effects near the event horizon. Pairs of virtual particles pop into existence.
Particle-antiparticle pairs.
Exactly. And sometimes one falls in while the other escapes. The escaping particle carries energy away.
Okay. And the source mentions angular momentum playing a role here, too.
It does. Most of the particles that could potentially escape, actually have high angular momentum.
The spinning ones again?
Right. And remember, they have a harder time getting over the barrier, so most of them just get deflected. They kind of ricochet off the black hole's gravitational field.
So they try to leave but just get bounced back, like trying to get out of a crowded room and just bumping into people constantly.
Something like that, yeah. It's only a really tiny fraction, the ones with very, very low angular momentum.
The swaves again?
Like the swaves, yeah. They have a real, albeit small, chance of escaping the pole altogether.
And that faint stream of escaping particles is Hawking radiation.
That's it. And for big black holes, it's incredibly slow. Just a whisper of energy coming from something we think of as total darkness.
It really challenges our whole picture of what a black hole is.
Fundamentally.
So this idea of black holes losing energy, losing mass through Hawking radiation, does that connect to their entropy? That's another big concept.
Oh, absolutely. They're fundamentally linked. When we talk about a black hole's entropy, we're essentially asking how much hidden information, how much complexity is inside.
Complexity. But don't they seem really simple from the outside? Just mass, spin, charge?
That's the paradox. From the outside, yes. But the entropy suggests that internally, there's a vast number of possible microscopic quantum configurations
Microscopic states.
that could all look like that same single macroscopic black hole we observe. Entropy counts those states. It's a measure of that hidden internal complexity.
So, like my sock drawer. It looks like one messy drawer from the outside.
Yeah.
But inside, there are a million different ways the socks can be jumbled up to create that mess. High entropy.
That's actually a wonderfully relatable analogy. Just scale it up. Way, way up.
To cosmic levels.
To the extreme. The number of these microscopic states for a black hole is given by this famous Wittgenstein-Hawking formula. It involves its surface area, basically.
Okay.
But the key thing is the number of states isn't just the value from the formula, it's exponentially related to it.
Exponentially. So like E raised to the power of the area.
Pretty much, which means the number is, well, it's staggeringly huge. Colossal. It hints at this hidden universe of complexity inside something that looks so simple.
Exponentially colossal. Okay, my brain just did a little flip. So a seemingly featureless black hole is just teeming with hidden possibilities.
Exactly. And the source also mentions level density.
Right. What's that?
That's basically just another way to quantify this immense complexity. It tells you how many distinct quantum states exist within a tiny, tiny range of the black hole's mass.
So if you added just a speck more mass,
you'd suddenly have access to an exponentially larger number of new possible internal states. It reinforces just how much is hidden inside.
okay, I think I'm starting to connect the dots. It's not empty space, it's this reservoir of potential states. Now, back to Hawking radiation. If they're constantly leaking energy...
they lose mass.
Right. So what happens eventually? Do they just disappear?
They evaporate, yes. Because they're radiating energy, they're losing mass. It's incredibly slow for big black holes, but it happens.
And the bigger they are, the slower they shrink.
Exactly. The rate of mass loss is inversely proportional to the square of the mass. So bigger mass, much slower evaporation.
So a supermassive black hole, like the one at the center of our galaxy, it's going to take practically forever to evaporate.
Oh, vastly longer than the current age of the universe. Unimaginably long.
But maybe tiny primordial black holes could have evaporated by now.
That's a possibility people explore, yes. If tiny black holes were formed in the early universe, they might evaporate much faster, maybe even ending in a final burst of energy.
Like cosmic ice cubes slowly melting away.
That's a nice image for it, over cosmic time.
Now, our source also talks about charged black holes, adding electricity to the mix. How does that change things?
Charge adds a really fascinating twist. These are called Reisner-Nordstrom black holes.
Okay.
And the big difference is, unlike uncharged ones, charged black holes can't necessarily evaporate completely.
Wait, they can't. Why not?
They can reach a stable minimum size, a kind of endpoint where the evaporation stops. It's like they hit a floor.
So they shrink down to a certain point and then just stay there, like a built-in off switch for evaporation.
Essentially, yes. The electrical charge fundamentally changes the space-time structure around them. They actually end up with two horizons.
Two horizons, an outer one and an inner one.
Exactly, which makes their internal structure and behavior much more complex than the simpler, uncharged Schwarzschild black holes.
Double the horizons, double the complexity.
You could say that. And there's this important idea of an extremal black hole. That's where the charge is basically maxed out relative to its mass. The charge is so large it perfectly balances the gravitational pull in a specific way.
So gravity pulling in, charge pushing out, sort of?
In a very loose sense, yeah. These extremal black holes are theoretically stable. They wouldn't evaporate.
Wow. So they could just hang around forever.
Theoretically. And the source even mentions a condition for practically stable charged black holes. If their charge is absolutely enormous, they'd be so resistant to losing that charge that they'd essentially be permanent.
So, while uncharged black holes might eventually vanish,
their charged cousins could stick around, like little cosmic batteries holding their charge.
okay, that's a neat difference. Now, the source takes a bit of a turn here into something called Rindler space. This feels like shifting gears a bit.
It is, but it's a really insightful detour. Rindler space isn't about black holes directly. It's about what an observer sees if they are constantly accelerating in perfectly flat, empty space-time.
Accelerating in empty space.
Yeah.
Okay.
The surprising thing is, even without any massive object creating gravity, this accelerating observer perceives a horizon.
A horizon. Just from speeding up, how does that work?
Well, imagine you're in a rocket, constantly firing its engine, accelerating faster and faster.
Right.
Light signals from things far enough behind you might never catch up because you're constantly moving away at an increasing speed.
So there's a point beyond which light just can't reach you.
Exactly. That boundary, the edge of the region you can ever get signals from, acts like a horizon for you. It's called the Rindler horizon.
So your own motion creates this boundary.
Your acceleration does, yes.
Oh.
For you, the accelerating observer, your patch of space-time seems self-contained, and other regions become sort of causally disconnected, like a blind spot created by your acceleration.
Wow. Okay, that's a head-scratcher. Acceleration creating an information boundary in flat space. And this connects to quantum fields and temperature.
It connects in a really profound way. Here's the kicker. A detector that's uniformly accelerating through what a stationary observer sees as a perfect vacuum.
Empty space.
Right. That accelerating detector will actually click. It will detect a thermal bath of particles.
It detects particles that aren't there for the stationary guy.
Precisely. The acceleration itself effectively heats up the vacuum from the perspective of the accelerating observer. This is the UNRA effect, and the temperature is called the Rindler temperature.
So acceleration is equivalent to temperature somehow.
There's a deep, deep connection there. Acceleration, horizons, thermal effects, they seem intrinsically linked, even without gravity.
So the accelerating observer feels like they're in a warm bath of particles, while the stationary one sees nothing. That's bizarre.
It is, and the source notes that some things you might measure in Rindler space are sensitive to what's happening right near that Rindler horizon, while others aren't.
Okay, like what?
Well, things like how quantum fields correlate far from the horizon behave nicely. But other quantities, like the entropy of the vacuum state, as seen by that accelerating observer,
The entropy again.
yeah, that can actually become infinite if you don't assume some sort of fundamental cutoff, some limit right at the horizon. It gets very singular there.
So some measurements are really sensitive to that edge, that horizon.
Very sensitive. Even the energy levels of a hypothetical thermometer carried by the observer depend on their acceleration. It all points to this thermal nature.
Okay, so horizons, whether from gravity or acceleration, are tied to temperature and quantum fields. This feels like it's building towards something big, like the holographic principle.
Exactly. That's often where these discussions lead. The holographic principle is, well, it's one of the most mind-bending ideas out there.
What's the core idea? In simple terms, if possible.
Okay, at its heart, it suggests that everything you need to know to completely describe a region of space, all the information,
Yeah.
might actually be encoded not in the volume of that space, but on the surface, the boundary that encloses it.
Wait, like a 3D movie being stored on a 2D screen?
That's a fantastic analogy, yes. Like the information content isn't proportional to the volume, as you'd intuitively expect,
All right, more space, more stuff, more information.
but instead it scales with the area of the boundary. It suggests the universe might be, in some sense, a giant hologram.
A hologram. So the 3D reality we experience could be projected from a lower dimensional surface somewhere.
That's the radical idea. It implies that the fundamental degrees of freedom, the ultimate pixels of reality, might live on a boundary surface, not throughout the volume.
Volume versus surface area for information. That completely flips intuition on its head. And does this connect to that ASCFT thing?
It does, very strongly. ADA-CFT is perhaps the most concrete realization of the holographic principle we have.
Okay, break that down a bit. ADO-CFT.
So ADA stands for anti-de Sitter space. It's a specific type of space-time geometry, one with negative curvature. Think of it like a saddle shape, but in higher dimensions.
Okay, a weirdly shaped universe.
Kind of. And CFT stands for conformal field theory. That's a type of quantum field theory with special symmetries, one that typically lives in fewer dimensions. The ADA-CFT correspondence is this proposed duality, this equivalence. It says that a theory of gravity happening in the bulk of this AD-S spacetime
Inside the volume.
is completely equivalent to a non-gravitational quantum field theory, the CFT, living on the boundary of that spacetime.
So it's like having two totally different descriptions, different languages for the exact same physics.
Precisely. One with gravity in, say, 5 dimensions, and one without gravity on its 4-dimensional boundary. Everything that happens in one theory has a direct counterpart in the other.
That's incredible, like a dictionary between gravity and quantum field theory.
In a sense, yes. The source mentions a specific example from string theory involving a 10-dimensional space, 8s5 cross s5. The point is, its boundary has fewer dimensions, supporting this holographic idea.
Mind-boggling. Almost suggests gravity isn't fundamental, but maybe emerges from quantum interactions on this boundary.
That's one of the profound implications people are exploring, yes.
Okay, wow. Let's try and bring this back to black holes and information.
Yeah.
We know quantum mechanics says information can't just be destroyed, right? It has to be conserved.
That's a cornerstone principle, yes. Quantum evolution is unitary, meaning information is preserved.
So, what happens to the information that falls into a black hole? Especially if the black hole evaporates via Hawking radiation.
And that is the core of the black hole information paradox. It's arguably one of the biggest puzzles in fundamental physics.
The paradox being?
If the black hole evaporates completely, and if Hawking radiation is purely thermal, just random heat.
With no details about what fell in.
Exactly. Then it seems like the information about what made the black hole is just gone, erased from the universe.
Which violates quantum mechanics?
Which violates quantum mechanics, a major crisis.
So the universe gets amnesia. That can't be right.
It really feels like it can't be right. Our source mentions this idea of information retention time,
Yeah.
how long it might take for the information to somehow get out.
Yeah.
And it also hints that maybe our standard way of thinking about quantum fields on a fixed curved background, maybe that's just not good enough near the horizon.
Our tools might be breaking down.
Perhaps. Maybe understanding the finite entropy, the holographic nature, is key. That fixed background approach might be missing something crucial about how information behaves near the horizon itself.
Okay, so the solution might involve these deeper principles like holography. And finally, the source just hints at something called black hole complementarity. What's the gist there?
Right, complementarity is one proposed resolution to the paradox. It's a bit subtle.
Try me.
It suggests that there isn't one single universally agreed upon story of what happens to the information. It depends on who's watching.
Different observers see different things.
Kind of. For an
Yeah.
observer outside the black hole, they might see the information get sort of scrambled and thermalized at or near the horizon and then slowly leak back out encoded in the Hawking radiation over immense timescales.
So, from the outside, information eventually gets out. Scrambled, but out.
That's the idea. But for an observer who actually falls into the black hole,
Right.
they might experience nothing dramatic at the horizon. They just fall through, carrying their information with them until they hit the singularity.
Those sound contradictory. Does the information stay outside or fall inside?
That's the complementarity part. The argument is that no single observer can ever actually verify both outcomes simultaneously. You can't be both outside watching the radiation and falling inside.
So because you can't confirm the contradiction, maybe it's not a real contradiction.
That's the essence of it. The extreme physics near the horizon, like extreme time dilation or redshift, might conspire to make these two perspectives consistent, even though they sound different. It's a way to save information conservation.
Okay, so two different stories.
Yeah.
Both potentially valid from their own viewpoint, resolving the paradox.
Yeah.
Wow. Okay, let's try and pull these threads together. This has been quite a journey.
It really has. I mean, we started with just asking what happens when you fall in. And we ended up talking about quantum tunneling, leaky black holes radiating energy.
Hawking radiation.
Yeah.
And their incredible entropy hinting at this vast hidden complexity.
Exactly. Billions and billions of internal states hiding behind a simple exterior. Then charged black holes, which might not even evaporate completely.
The stable ones.
And then Rindler space, showing horizons and temperature, can pop up just from acceleration.
Connecting motion and heat in flat space.
Which leads us to the really big ideas.
Yeah.
The holographic principle.
Information on the boundary, not the volume.
And its connection to things like ADA-CFT, potentially linking gravity and quantum theory, and all of this circles back to the information paradox.
How does the universe keep track of everything, even when black holes are involved?
It's a whirlwind tour, but it shows black holes aren't just simple drains. They're dynamic, complex objects at the heart of physics' deepest questions.
Absolutely. And it leaves you with this final thought, doesn't it? Considering that immense entropy, that holographic idea, what does it really tell us about reality? About information? Are black holes the ultimate destroyers? Or are they maybe? Maybe incredibly dense archives, storing information in some bizarre, scrambled holographic way we're only just starting to guess at.
It's a profound question. Are they cosmic shredders or cosmic hard drives?
Yeah. It's a deep dive that definitely leaves you thinking about the fundamental fabric of everything. And that, I think, is where the really exciting science is happening.